Welcome back to our ongoing look of graphs of trigonometric functions. And when we left off, we had a lot of stuff just thrown onto our plate. Whoever did that should be ashamed of himself. Right? We ended with these three disparate goals that might be pretty hard to accomplish based on your current background knowledge of functions and function transformations. There's going to be quite a bit to do here. We will take each of these goals in turn, and we will see what we can do with each of them. Now, before we get into that, and there will be two transformations that we have to look at just for this one, this first one here, which we'll do in this video. But before we do that, I do want to introduce a slight change in the usual notation we've been using. You see, up until this point, we have been looking at functions in t, in essence, right? We've had sine of t and cosine of t, where t was the number about which we moved on the unit circle. Well, now I want to stop doing that and start calling it y is sine x, and g of x or y is cosine x. So I want our independent variable, instead of being t, to start being x. Reason being, that is the general way people deal with functions in pre-calculus and calculus for that matter. Our independent variable historically tends to be x, for reasons because we do it, I guess. Now the transition is not going to be that awkward, although you will have to do a double take at least once when you see something like this. Because you say, okay, cosine x. So I'm going to move x on the unit circle, and then my x coordinate after having moved x is going to be my output. And that sounds a little awkward, and I understand that. But at the same time, what I want you to be able to do, if not that you already have been able to do it, is to start dispensing with the notion of moving on the unit circle entirely and just have it be second nature. Because when I ask, okay, what's the cosine of pi over 6? Hopefully, we're starting to think less and less about the unit circle and just be able to say resolutely, oh, it's square root of 3 over 2. And similar for sine, if I ask what the sine of 6 pi over 3 is, well, that's 2 pi. That's a bad example. It's 0 all the same. But hey, I want us to be able to stop thinking about moving around the unit circle as much as possible and just be able to get to the meat of the matter. Partially because if we keep having to trace our path on the unit circle every single time we're evaluating sine or cosine, first of all, we're going to start getting bogged down in our computation. And second of all, stuff like this, talking about functions in x or functions in y, if we ever did that for whatever reason, which is going to happen also now that I think about it, that will be a little more confusing. So let's try to start move away from that and just be able to put some number into sine and get some number out without having to stop and think about what the label that number carries when it goes in. All right, enough about that. Let's get into our goal here. I've got sine and cosine normally bounce between plus or minus 1, but now I want to bounce between 2 and 7. I want that to be the behavior my function models. So I want my function maybe to look like 2 sine x, or sine x plus 7, right? There's a 2 and a 7 in there. Maybe a 2 or a 7 pops up in our final function equation. So let's just throw those in there and see what we get. All right, so here's sine x normally. And here is double that, right? 2 sine x is sine x doubled. All my outputs from sine x, I now multiply by 2. So what was 0 before is, well, still 0. What was 1 before is now twice that. What was negative 1 before is now twice that. And everything in between has also been doubled. So now let's see, I go between plus or minus 2 now. Well, I hit the 2 at least, so that's good. But I'm definitely not going between plus or minus. Well, I guess not even plus or minus, but between 2 and 7. I'm not doing that. I need to do more. But I'm probably going to have to do something like this. The other thing I want us to try is sine of x plus 7, which is actually up here now. And if you stop and think about it, that shouldn't be terribly surprising either, right? Some number x comes in, sine comes out, and then I add 7 to whatever I had before. So sine of 0 was 0 before, it's 7 now. Sine of pi is 0, well, it's still 7. Sine of pi over 2 was 1 before, now it's 8. Right, let's look at that. And then sine of 3 pi over 2 is -1. Well, now it's 7 more than that. It hits 6. So all of the points that we would have normally gotten for y equals sine x, we've now essentially shifted up by 7. Now, a little bit of vocabulary before we start summing this thing up. I've got this line of not quite symmetry, but it's a median line, a lot of people call it. This line, y equals 0, is the so-called median line of the y equals sine x. Up here, the median line is y equals 7. That's because that's the middle point about which the sine waves will bounce. So that's important because, well, normally it was 0, but when I added 7, it became 7. So this number directly influences where my median line is. This number, the 2, being multiplied on, directly influences how wide, what range my sine graph can cover. There's a word for that too. Specifically, the distance between the median line to the peak, or the trough, whichever, the distance from here to the max or the minimum is called the amplitude. Not the overall width of the wave, just from median line to peak or median line to trough. So with that in mind, let's sum up what we have and see if we can use both of these in tandem to produce the graph we want, bouncing between 2 and 7. So, if we have some number being multiplied onto sine x, or cosine x for that matter, or I guess any function if we're going to be honest with ourselves, normally that has some range to it. Normally it has some range, but if I multiply it by 2, it doubles. If I multiply it by 3, it triples. If I cut it in half, well, the range gets cut in half. And so this value a is the value of what we call the amplitude for sine and cosine. So instead of bouncing between plus or minus 1, it now bounces between plus or minus a. And also, as I mentioned before, adding some number at the end just shifts your median line, and by extension all the other points as well, by that number. So respectively, we have a vertical stretch because we are stretching our graph, and we have a vertical shift because we're moving everything up or down. Those are the words we use to describe these things. Now, before we get too trigger happy with saying the word amplitude and median line, let me go ahead and say this, and I'll probably have to say it again, but amplitude and median lines, those things apply exclusively to sines and cosines. As we'll see when we graph tangent and cotangent, and even secant and cosecant if I feel like it, none of those things really have amplitude, because they have no maximum and no minimum. We still call those changes to tangent, if we do something like this, a vertical stretch, but it doesn't have an amplitude. And no one really refers to the median line of tangent. I guess you could, but no one does. So these vocabulary words we are exclusively going to apply for graphs of sines and cosines. Alright, well, enough of that. Let's get to the meat of the matter. I need to bounce between 2 and 7. So I need to find the median line, and I need to find the amplitude that will make that happen. And those values is, well, halfway between the peak and the valley is your median point. So I just take the average of 2 and 7, and I get 4.5. So I need my vertical shift, I need my median line to be at y equal 4.5. So I'm going to add 4.5 to my sine x function. So I need to go from 4.5 to 2 and 7. So I need to move a total of 2.7 away from the median line, or 2.5 away from the median line. So my overall function has amplitude 2.5 and vertical shift 4.5. The overall function equation is going to be called 2.5 sine x plus 4.5. Amplitude, shift. So I have just now one last question. What if things are negative? Because you can multiply anything you want onto a function equation. You can add any number you want. That includes negative numbers. So let's stop for a minute and analyze what happens for negative things. And actually, we'll not worry too much about this. I'll let you think about this on your own. See if you can answer what each of these do in turn after I show my thing. You see, what I have here is actually a nice interactive. See, here's sine x. And I've got something multiplied here and added at the end. Don't worry about this stuff in between quite yet. We'll get to that, I promise. And we saw that if we multiplied sine x by some number, that determines what its amplitude is. But we've only talked about positive things. What if I multiply it by something negative? Well, what happens is you still change the amplitude by that amount, but you're also multiplying everything by -1. So what was positive becomes negative. What was negative becomes positive. And what was 0, well, stays 0. So what we have with a negative amplitude is, well, positive amplitude, but now what you might refer to as a reflection about the x-axis. Simpler put, all we're doing is taking everything that was positive, it's now negative. You can call whatever you can use whatever words you want to describe that behavior, but that's all we're doing with a negative amplitude. Additionally, this one's probably simpler to explain. If I add some number, I shift the whole thing up because I'm taking all my outputs and adding something to it, making them higher. Conversely, I shift everything down if I subtract a number at the end. So that one's pretty self-explanatory. You either shift up with positive, shift down with negative, nothing fancy there. And amplitude, you either have your normal uppy downiness or downy uppiness, depending on if it's positive or negative. And you cannot quote me on that because that's embarrassing. Pretend I never said that. Or don't. You're a grown person, you can do whatever you want. So based on that, hopefully we're able to say what happens for each of these. And maybe stop and think about that for a minute. Okay, I got to shift down. I've got what would have been this before, except now going up and down. It goes down then up. And then this is just like this guy, having been shifted down, but now it's got downy uppiness instead of uppy downiness. I need to stop saying that. At any rate, we now have two basic transformations at our disposal. We can shift and we can stretch, both in the vertical direction. We'll worry about horizontal stretches and shifts later, but we can do everything we need in the vertical direction. And also we have a general awareness of what happens if we have negative amplitudes or negative shifts or negative stretches. So that, I think, is a good stopping place as any. In class next time, we will start to be familiarizing ourselves with these two transformations, and then going forward, we'll add a few more to the mix. So let me know what you need me to talk about or want me to talk about before we get into class proper next time. Just fill out the question we have coming up, and I will see you in class. You guys have a good rest of your day.